you're chasing the lead, you can make a couple of birdies on these holes. We've seen it 3 or 4 times today from the earlier players. But if you're protecting the lead, it is such a great finish. Anything can happen, as we've seen here with Paul, in those 3 holes. Well, you think about Bubba.
This golf is really boring. Want some coffee?
Sure.
For 3 to, at that time, tie the lead with Paul Casey. And now Casey has 1 hole to play. He's 3 behind. Really, this is it. This doesn't drop. This doesn't.
Cream or sugar?
Nah, black please.
Oh, no problem, bro.
Well, we're at 82, carry to the front, 92, 82.
Thanks, man. That's a good cup of coffee.
Nice fresh pot. Enjoy. Huh. 80 degrees Celsius. It's too hot. Oh man, are you alright? That was like 80 degrees.
I wonder how long it's gonna take till we can drink this.
Let's talk about that. You know, when I think about it, we can use Newton's law of cooling to determine how long it will take for our coffee to cool to a drinkable temperature.
Cool.
You know, according to Newton's law of cooling, the temperature of a cooling object drops at a rate that is proportional to the temperature of an object minus the temperature of the surrounding medium,
Interesting.
providing that the temperature of the surrounding medium remains constant.
Until he knew for sure he had the win. So it's down to this swing.
Bravo. But that just gives us the rate of change of temperature. We need to find the total change of temperature.
Well, in order to find the total change of temperature over the change in time, we will have to take the integral of our equation.
Newton's law of cooling states that the change in temperature with respect to the change of time is equal to the negative constant of proportionality times the temperature of the object minus the temperature of the surrounding air.
Possibilities until he knew for sure he had the win.
So, we must take Newton's law of cooling and rearrange it so that temperature is a function of time.
This doesn't go in.
First, we will isolate the temperature's terms on the left side, and then the other terms on the right side. The next step is to find the integral of each side. So then isolate temperature as the equation of E to the power of negative K T plus C plus ambient temperature. So here we are. We've isolated our T terms, our temperature terms, on the left side, and moved over our time to the right side.
The antiderivative of 1 over temperature minus ambient temperature is going to be ln of temperature minus ambient temperature. The antiderivative of the constant of proportionality times the change in time is the constant of proportionality, because it's a constant, times the time, plus a constant that we get when we're taking an antiderivative, which is this c here. Now, because we've got ln of t minus ta equals negative kt plus c, we can say that e to the power of negative kt plus c is equal to the absolute value of t minus ta. Now, using exponent laws, we can see that e to the power of negative kt plus c is equal to e to the power of negative kt multiplied by e to the power of c, which we replace with just c as that is a constant, since E and C are both constants. So our final term is C times e to the power of negative kt. Now, to address these absolute value bars, since the temperature of T is generally going to be hotter than the ambient temperature, we can kind of drop the absolute values, since a greater temperature minus a lesser ambient temperature will give us a positive answer. Now we'll move ambient temperature over to the right-hand side of the equation, and what we're left with is that temperature as a function of time is equal to our constant C times e to the power of negative kt, with k being our constant of proportionality, plus our ambient temperature.
So, as we know, the initial temperature of our coffee is 8 degrees Celsius, as per thermometer in our coffee. And now after 1 minute, it's now 7 degrees. And the current ambient temperature is 20 degrees Celsius. Do you know what the best temperature to drink coffee is? Everyone knows that. 60 degrees Celsius. Oh, duh. So to find C, we use our initial temperature at a time of 0 and our ambient temperature of 20 degrees Celsius. So if we plug in the T of 0 is equal to 80 degrees, here we have 80 on the left side, and then a time of 0 in the time variable, and then our 20 degrees into the ambient temperature, and then simplify. E to the power of negative k times 0 is just e to the power of 0, which is going to be 1. So 1 times c is just c, and we get a value for c of 60. So now that we've found a value for c, we can then plug in our temperature at 1 minute, our ambient temperature, and our time of 1 minute into this equation again to find a value for k. Here we have our plug and chug of all the values, and eventually you end up with k being about 1.09. Now that we have our equation of temperature in relation to time, we can find the amount of time it'll take to get our desired temperature of our coffee to drink. This is the optimal temperature to drink coffee at. That's why we are finding the time of it. So we know that the temperature we're looking for is 60 degrees. We have our constant now for C at 60. We have our ambient temperature of 20 degrees that we can plug in, and we have our K value, our K constant. So when we plug in these values, we end up with these equations, and simplifying and a little bit of algebraic manipulation, we pull everything down to here. We know that the natural log of E is just the exponent. So take the natural log of both sides and work your way down to natural log of 2/3 over the natural log of 5/6. And the like a rounded value of t is 2.22 minutes, or 2 minutes and 13 seconds.
Now that we've used the differential equation to determine that after exactly 2 minutes and 13 seconds, our coffee will be optimal drinking temperature, you ready to have a sip?
I'd say so. Cheers, mate. Now we can really enjoy this golf.